Hi, this is Mr. Companion. Have you ever wondered why the sound of an ambulance's sirens increase in pitch as they approach your location? And have you noticed that they decrease in pitch as they move away? Here's the same phenomenon, but this time it's a car passing by with its horn blaring. Today we're going to simulate the motions of an aircraft emitting sound waves, and we'll see how the properties of those waves change. In previous lessons, you've learned that all waves, like light and sound waves, can have different wavelengths and frequencies. With sound waves, we can hear the frequency of those waves as pitch. So what exactly is Doppler effect? Well, the definition is an increase or decrease in the frequency of sound, light, or other waves as the source and observer move toward and away from each other. So now that we know what the Doppler effect is, let's use the simulation found in today's lesson and measure these changing waves. So let's take a look at today's lab. You're going to follow the link that's in the PowerPoint or that your instructor has given you to bring you to this site. This lab will focus on the changes to wavelength, period, and frequency that occur from moving sources of waves. When you're ready to start the experiment, click the Begin button below. Let's do that. So once you click the Begin button, you've been given to this grid plane here. You'll notice that you have both blue and gray lines, and then an even finer set of lines in this grid. So the blue lines are separated, as you can see here, by 100 meters. The gray line is 50 meters away from the blue line, and each of those smaller, thin gray lines are 10 meters apart from each other. This will make measuring your sound waves a little bit easier. So what exactly are we looking at? We're going to be looking at waves emanating from a flying object. In this case, it's an aircraft. You have three things on your screen at the bottom that you can adjust. First, you have the object speed, so the speed of the aircraft in meters per second. Wave speed, speed of the sound waves that are emanating from that object. And the frequency is measured in hertz. So here we have 1 hertz, which is 1 wave per second. Now, I'd like to take a moment to run the simulation and give you some example data to play with and show you how to measure the wavelengths. Now, I just want to clarify, this is not the correct answer to anything on your assignment. Basically, what I'm doing here is I'm just showing you how to do the measurements. So before we hit the start button at the top, I want to draw your attention to the bottom to those three variables that we have there. Each variable has a set of arrows, a large one pointing down, a small one pointing down, a small one pointing up, and a large one pointing up. For the two speed variables, you're looking at clicking on the large arrow to increase or decrease the speed by 10 meters per second. For the frequency, by clicking the large arrow up, you're moving up by 0.5. Clicking the large arrow down, you're moving down by 0.5. If you click the small arrow up, you move up by 0.1, and the small arrow down brings you down by 0.1. So now that we know how to adjust the variables, I'm going to adjust the object speed to 50 meters per second and the wave speed to 80 meters per second. I'm going to leave the frequency alone. I'm going to click Start. So now you'll notice that the object is moving from the left-hand side to the right. And in fact, I'm going to pause it. And you can see that waves are emanating from the vehicle. So it's an aircraft, and aircrafts have an engine after all, and that engine will release a sound. Now that sound that's coming off of there has a baseline frequency to it. But you'll notice that on the right-hand side, those waves are accumulating, and on the left-hand side, they're spreading out. All right, so I've taken a small screen capture of our simulation just so I can draw on it and to possibly make the measurements a little bit more clear. So you can see that on the right-hand side, many of the waves have bunched up, and on the left-hand side, many of the waves have spread out. So we'll be taking a look at them, and I'll be marking off some of the spots where they are so it's a little bit more clear. So you can see this wave right here goes from about this spot right there to about this spot right here. Now, if we measure them, that's one, two, three lines apart. Now remember, each line equals 10 meters. So in this case, these are approximately 30 meters apart. Let's take a look on the back side of the wave, the one that's where the aircraft is moving from. So it appears that one of the waves ends right about there, and the other wave ends right about there. Move that over a little bit. And if we measure these, well, we know from here to here is 10 lines. That would be 11, 12, 13. Now, again, if we recall, each line represents 10. This would be 130 meters. And then lastly, we want to be able to measure adjacent to the aircraft. So we have one line that's right about here, and we have one line that's right about here. And if we measure these out, we should get 1, 2, 3, 4, 5, 6, 7, maybe about 8. So in this case, our distance between each wave, our wavelength, could be about 80 meters. So I hope this has been helpful. Before I go, I just want to pose a couple quick questions. What do you think would happen to the wavelength if we increased the frequency? And what could happen to the wavelength if we increase the wave speed? All right, that's it for now. I'll see you soon.